My name is Niek and this is my dear friend Albert Spruyt, and we are here to talk a little bit about fault injection attacks on secure boot. Today's talk will start off with some introductions for fault injection and secure boot, after which Albert will take over and lay out some bypasses of secure boot using fault injection, during which he will touch upon mitigation strategies and attackers' practicalities. One disclaimer here, we are not really talking about UV secure boot. We're really talking about proprietary secure boot implementations and implemented on secure embedded systems. We are both security analysts at Risker, where we test the security of different products and devices. And at Risker, the company is basically split into two parts. One unit is primarily focusing on making hardware in order to do side channel attacks or fault injection attacks. And the other unit, which we are part of, tests actually the security for all sorts of different clients, including secure boot implementations. And this talk actually shows a little bit of both of these units. First of all, I would like to start with a definition of fault injection. So when we talk about fault injection, we really mean that we can change the intended behavior of a target by injecting a glitch or a fault. For example, if you look at the following code, we can see that this code is used to open a door based on the validity of a key. So the idea is that using fault injection, we can change the intended behavior of this code construction. So that means if we can do this, and if we inject this glitch at the right moment in time, we can actually open this door with an incorrect key. But this makes you wonder, how can we introduce such faults? Well, the academia studied various different techniques, some of which are available to the masses, some are a little bit less available. For example, optical fault injection, you need very sophisticated tooling. But to give you an idea how voltage fault injection works, which is something that's available to the masses, we can see that there is a certain voltage signal provided to the target. And the idea is that we can inject a glitch or a dip in this voltage signal at the right moment in time, not too soft and not too strong, in order to change the intended behavior of the target without affecting its continuation. So after the glitch, the device operates as normal again. And the type of faults we can actually achieve using fault injection are very different. And to give you some ideas what type of faults are possible, we can, for example, affect hardware within the target. So for example, we can change the data that is stored in instructions or data that is actually transferred over a bus, so while it's in transit. Also, we can affect the subsystem that's responsible for executing software, for example, the ARM subsystem. And one thing we can do there is for instruction corruption. So what we can achieve is the first line of this snippet shows actually the original instruction, and using fault injection, we can change a bit in the instructions encoding in order to change this instruction to something completely else. And depending on the amount of bit changes, this can range from changing the operands or the opcode itself. And in similar fashion, there is actually instruction skipping, and that means that the original instruction is changed into a variant that has no side effect on the continuation of the target, other than not executing the original instruction. For example, we see here is that the contents of R1 originally went into R0, but the corrupted instruction moves the contents of R0 into R0. So how and why is this useful? Well, for example, if we look at this generic secure boot implementation or this generic embedded system, we see that there's three components. There's a system on chip that includes various different components. So there's a CPU, there's some ROM code, there's SRAM, and there's two external components. So there's a DDR chip to execute software from, and there's a flash chip to store the software on when the device is powered off. If you want to make this embedded system secure, you have a problem, because the integrity and confidentiality is not assured. And what we see is that the first stage bootloader is loaded into SRAM, which is used to initialize the DDR, after which the second stage bootloader is loaded into DDR. So this mechanism that actually assures the integrity and potentially confidentiality is typically referred to as secure boot. Secure boot can be implemented in different ways, and typically it can be different between these implementations. However, most of them follow a similar concept, is that there is actually a chain of trust implemented that is very similar to the PKI found in browsers. So they implement a root of trust using immutable code and key. So in this case, that is an internal ROM, so that is the first code that's executed after power on reset, and there's a public key, and both cannot change. They're fixed inside the system. And this code is actually used to load and authenticate the first stage from Flash. And a more sophisticated version actually also provides confidentiality, and that means that there's also a symmetric key available to this code, which can be used to decrypt the payload before it's authenticated. However, in reality, secure boot typically consists of multiple stages. For example, if you look at the ARM Trusted Firmware reference implementation, we see that there's multiple stages executed after each other, which all authenticate each other before they're executed, effectively implementing a chain of trust. And effectively, this is secure boot. But this makes you think, if there's multiple stages involved and there's software involved, then these implementations are likely logically flawed. It means that we do not need a hardware attack, but we can actually use a software exploit in order to bypass secure boot. And this is very true. And over the years, we've seen numerous examples where actually secure boot is bypassed in a logical manner. However, one thing to realize is that these boot stages are typically consisting of a small code base. And that means that the logical attack surface is not that big. And that means that there's likely implementations out there that are not logically flawed, and especially for more mature products. So in such situation, when you want to bypass secure boot, you need to resort to another attack. And one of those attacks is actually fault injection. However, there are some drawbacks for performing fault injection compared to software exploitation. For most of the fault injection techniques, we actually need to make modifications to the target. So that means that you have to be invasive. For example, if you want to do voltage fault injection, you need to make modifications to the PCB in order to supply your own voltage to the target. And also, for example, for optical fault injection, if you want to shoot a laser at the chip, you need to probably open the package with chemicals or something else. And also that means, because you need to apply certain tooling to the target, you need to have a physical presence to the target. And also, compared to software exploitation, it's typically a little bit more expensive because you need additional tooling other than your workstation or your laptop. However, the advantages are significant, and Albert will go into detail more about this. You don't really need a logical vulnerability to bypass secure boot using fault injection. And standard technology, so the embedded technology we are facing today, is not properly protected yet against the fault injection attacks. And especially it becomes relevant to use such a sophisticated hardware attack when there's actually assets available during boot which are not available after boot. Because after boot there's a lot of software actually executing, for example a Linux kernel, and the chances of this being logical fault is much higher. So some assets that can be available only during boot is, for example, the secure boot code itself. So for example the ROM code. It is common practice to, after the ROM code has finished executing, to map this out of memory. So if you break into the system using a kernel exploit, you cannot access this code anymore. And this code can be used, for example, to identify a logical vulnerability, or there might be secrets in this code available. For example, the decryption keys to decrypt the first stage from Flash might actually be in this code. And if secure hardware is used to perform this decryption, this hardware might be disabled after boot, or the keys that are used for decryption might actually be made inaccessible or unusable. And in order to perform fault injection, as mentioned, we need tooling. Nowadays, for several fault injection techniques, the tooling is becoming easier available. And that's especially due to some open source initiatives like the Chip Whisperer, which is an FBA-based platform which can be bought for a couple €100, I think. And this can be perfectly used to attack embedded systems. However, at Riskier we use our in-house tooling, which is commercially available, but both platforms, they are designed around an FPGA, which allows you to perform fault injection. And this tooling is typically used in a setup like this. There's a workstation, of course, where you have most of your software running that is able to communicate with the glitching device. So it provides instructions in order to what to do. And there's a communication channel towards the target. And the glitching device actually has a few inputs and outputs which are used to perform the fault injection attack. For example, if it's possible, the target can send a signal to the glitcher in order to tell the glitcher when to inject the glitch, which is very essential for fault injection. And of course, if you're doing a voltage fault injection, you want to have an arbitrary VCC signal that you can supply to the target. So that's the signal going into the target. And then whenever the setup is actually in an erroneous state, we need to reset the target into a known state. And this can be done using the reset signal, typically exposed on the embedded system itself. However, in practice, fault injection setup typically looks a little bit more like this. So we have the victim in the middle, and there's a whole bunch of different cables tied to the board in order to perform the fault injection test efficiently. So for example, what you see here is that we put a probe on top of the chip in order to take power measurements to have an idea what exactly is going on in the chip in order to time the attack. Because you have to realize that after boot, it typically takes quite a long while until the moment you want to glitch. And this actually helps you doing that. So this brings us to the end of the introduction, and I would like to give the word to Albert, and he will continue with his part of the talk.
Thank you. Okay, so Niek just gave us an introduction on secure boot and fault injection and how to make a setup. So let's now get started and let's try to actually bypass secure boot. At the end of the day, if you have a secure boot implementation, you're going to have to compare a computed hash against either a decrypted hash or a stored hash. And that immediately gives you a nice place to inject a fault. So, and this gives you a nice bypass of the authentication. So if the secure boot performs encryption, you will need to find another way to bypass that. So here we have a little bit of source code from the Mbed TLS project, as it is used in the ARM trusted firmware. And what we see here is we see a memory compare, which compares a hash against a decrypted hash. And if they're the same, we continue booting. And if they're not the same, we stop booting. Okay, so this looks like a pretty good place to inject a fault. However, this is C source code, so we compiled it just to see what it would look like. So here we see the call to memory compare, and if it's the same, we continue booting, and otherwise, we return an error. So, and here we can see a number of places where we can inject a fault. So we could try to skip the call to memory compare. Perhaps we could have an influence on the conditional branch instruction. Or perhaps we could do any of a number of other options. And what we see here is that when we have a single line of C code, and when we compile it, we actually get a number of places where a single fault basically renders secure boot ineffective. So there are actually multiple locations where we can bypass this secure boot check using only a single fault. Okay, so the code we just looked at is actually inside the Mbed TLS PK verify function. So here we have something looking quite similar, and here we actually pass in the hash and the signature. And this code looks remarkably similar, which probably means it will compile to something very similar as well. And this will mean that we can probably find a number of places where a single fault will actually be able to bypass the Mbed TLS PK verify call itself. And this means that these bypasses can basically happen on all levels. They can happen inside functions, they can happen inside their calling functions, and they can happen inside their calling functions. Okay, so that was the comparison, but what are we going to do when that comparison fails? Well, the classic answer is to enter an infinite loop. Okay, so let's have a look at that. So here we have exactly the same code. We have the Mbed TLS PK verify function, and we compare the hash against the signature. And if these are not the same, if these do not match, we go into this infinite loop, and otherwise we continue booting. So I mean, from C source code level, this looks okay, but what does this compile to? So we compile it. Here we see our Mbed TLS PK verify function. If we fail, we go into this infinite loop, and otherwise we continue booting. Now, there's something missing from this story, and that's that the infinite loop is actually directly above the correct code path to continue booting. And this means that if we manage to inject a single fault into any iteration of this infinite loop, we might be able to break out of this infinite loop and continue booting. Now, the nice thing for the attacker here is that timing is not an issue. We only have to hit one iteration of that infinite loop. Okay, so it should be noted that this is actually a classic smart card attack, and in general, if you detect that something is incorrect, it's probably better to reset the entire chip or basically to wipe cryptographic keys. Okay, so these were some examples of some classic bypasses, but vendors have also started to implement mitigations. So these mitigations can be either hardware countermeasures, where the goal is to detect the glitch as it's being injected, or to detect faults when they have already occurred. It's also possible to use software countermeasures, and software countermeasures can only actually detect the fault when it has occurred. And the goal is to lower the probability of such a successful fault. However, because they can only detect the fault when it has occurred, they do not really address the root cause of this issue. And you can lower the probability, but you cannot completely rule it out. Okay, so we just discussed some examples of some classic bypasses, and we discussed some of their mitigations. However, the attack surface is larger. So let's start with combined attacks. Okay, and the combined attack, what we define as a combined attack, is basically you take fault injection and you use the fault injection to construct a logical vulnerability. It's basically build your own buffer overflow. And for this example, we're going to take the easy approach, and we're going to change the size argument of a mem copy. So to illustrate, before the corruption has occurred, we're going to copy 1000 hex, and after the corruption, we're going to copy more data. And hopefully we're going to overwrite some critical variables, for instance the stack perhaps, and we'll be able to introduce our own data and then execute our own code. So the nice thing about this attack is that it actually works even when dedicated hardware is used. So in this example we've used memcopy, but this also works, for instance, if a call to a DMA engine is used. Okay, so how does this work in practice? Here we have the secure boot system as detailed by my colleague Niek. The bootloader 1.1 will go into SRAM, and the bootloader 1.2 will go into DDR. But there is something Niek didn't say, and that actually the SRAM also contains the stack of the boot ROM. So I think most of you can already see where this is going. Okay, so here is our code that's running on the CPU. Here we set up the parameters and then call memcopy. So we've prepared the contents of flash, we've prepared a suitable payload, denoted by C, followed by a lot of pointers. And then when the system boots, when this code runs, we'll try to introduce a fault, hopefully changing the size argument, corrupting it, and hopefully we end up overwriting all of the SRAM, and hopefully the pointers will overwrite the stack. And then when the function returns, it'll take one of these pointers and we'll directly jump to our own code. So the thing you have to realize here is that during these early stages of boot, typically there is no normal exploit mitigation. There is no ASLR, there are no stack cookies, and execute is not enabled, it's not available. Okay, so for our next combined attack, which we call the wild jungle jump, and the basic idea is you start glitching basically after the device has started to copy memory, to copy the flash contents, but before it has fully decrypted the image or before it's fully completed the RSA computation. And the idea is basically to start glitching, and hopefully we'll jump directly somewhere close, directly to our payload or close to it. And this actually works in practice, and this works in practice because there are a lot of magic pointers around, and these point basically quite close to our code. And we can get these magic pointers from anywhere. We can get them from the stack, from registers, or from memory. And the more magic pointers are available in the system, the higher the probability of a successful bypass. So let's summarize these combined attacks. So they allow you to actually bypass both the authentication and the decryption of images. And typically, little software exploitation mitigation is implemented during the early stages of boot. And fault injection mitigations in software may not be entirely effective. And in the end, the possibilities for combined attacks are pretty much endless. Okay, so we made it sound very easy. We said we have a generic secure boot system, but there are some practicalities that the attacker has to overcome. So first of all, the attacker needs to prepare the target. So as my colleague Niek said, sometimes that means soldering wires to your PCB, but it can also mean using acid to decap chips, to remove packaging from chips. So you can use optical fault injection, which means lasers. Finally, so we also need to find the timing of the glitch. So the moment we actually introduce the fault. So we can try to take, for instance, power or EM measurements here. We can take a measurement of a normal boot and then of a corrupted image, and these will exhibit different characteristics. And in this way, we can narrow down where we need to inject the fault. So we need to not just only find the correct time to inject the fault, but we also need to find the right glitch shape. And the glitch shape depends quite a lot on the method you're using to inject the fault, but for fault injection, this can be the glitch voltage you want to introduce, but also the glitch length. So together, this is actually quite a large parameter space which you have to search. And finally, you of course need to prepare an image that you wish to boot. And depending on where you want to introduce the fault, you may need to make a different image. So in conclusion, today's standard technology is not resistant to fault attacks. However, there are a number of ways in which we can minimize this attack surface. So manufacturers need to authenticate all code and data coming into their system. They can try to minimize the code size of early boot stages, giving less attack surface to actually perform fault injections on. And we also need to, manufacturers also need to draw privileges at an early stage. If certain keys are only available in the ROM boot stage, breaking the secure boot chain later has no effect. We can also try to lower the probability of a successful bypass. So that means, for instance, implementing the fault injection countermeasures we discussed. But it can also mean implementing software exploitation mitigations to have a higher degree of protection against these combined attacks. However, in the end, the robustness of a secure boot implementation can only be determined using testing. Okay, this was our presentation. So if you have any questions, I know most of you want to head off to lunch, so if you can also catch us later. But maybe we can do some questions now.
Are there any questions? I've got the mic over here, so just give me a sign.
Yes?
So I wonder if you tried this kind of attacks on like iPhones, for example, and did you, find any mitigations to that?
So this is a target-specific question, and I'm going to have to politely decline to answer that.
For the glitching, is this the spider enough, or do you need even more things there?
I think in the basis it's enough. It depends a bit on your target. I think it also is a question of what the target needs. So you can imagine that if you have a normal embedded system, you might need, an FTDI cable. It depends a bit on how much power the target draws, but you might need basically a source that can deliver the amperage needed for that target. So basically you need all your normal interfacing stuff, but you can it's also probably a good idea to have an oscilloscope ready, because you also want to take power measurements to determine when the best moment is to inject a glitch.
Maybe after the talk we can talk more about details to see.
Anyone else with a question? No, then I'd like to thank both Niek and Albert for their talk.
Thank you.
And as was already mentioned, now there's time for lunch. We will continue here for both attendees here and for our live stream in 1 hour, which is 2 o'clock Amsterdam time. See you hopefully then.